Hi, it's Kate, and this is the fourth and final video for week 6 of Math 23. Well, now we know a little bit about series. We know what it means for a series to converge. Remember, that means that the limit of the partial sums exists and is finite. Let's talk a little bit more about convergence tests, how we can take a look at a series and determine whether it converges or not. Frequently, it's very, very difficult to find what it converges to, but we usually can tell whether or not it converges. And for most of our purposes, that's what matters. Well, first things first. If a series converges, the limit of the terms is 0. Again, limit of the partial sums exists and is finite, but the limit of the terms is 0. The first thing that we can use to determine whether a series converges is the comparison test. Say you have a series, I'm going to call it the A series here because it's just much easier. We're calling this particular series A sub n is all its terms, and it's all positive. Well, if the A series converges and the absolute value of B sub n, the terms in the series B sub n, so the absolute value of the terms in the series are all less than or equal to the terms of the A series, for all n, then the B series will also converge. Note that if the A series diverges to positive infinity and the absolute value of the B terms are always greater than their corresponding A term for all n, then the B series will also diverge to positive infinity. What's important to note is that it is only one side of the inequality is useful. For instance, if you have two series where you know that one is term by term less than the other, and the greater one diverges, you don't know anything about the one that is term by term less than that one. It could diverge too. It could converge, you just don't know. But if you have a series that is term by term less than another series that converges, then you can conclude that it also converges. Similarly, if your series is term by term greater than a series that converges, you don't know anything. Your series could converge, your series could diverge, who knows? But if you're term by term greater than a series that diverges, then your series will also diverge. Here's the ratio test. Again, we have our series A sub n of non-zero terms. And this series converges if the limit supremum of the absolute value of A sub n plus 1 over A sub n is less than 1. Similarly, the series diverges if the limit infimum of the absolute value of A sub n plus 1 over A sub n is greater than 1. And if the limit infimum of A sub n plus 1 over A sub n is less than or equal to 1, which is less than or equal to the limit supremum of A sub n plus 1 over A sub n, then you have no information at all and you need to perform another test to determine convergence. This is why it's really important for you guys to be going back and thinking and making sure that you have vocabulary solid, because if you aren't really clear on what the limit infimum is or the limit supremum is, then this definition can be really, really confusing. This test can be confusing. But again, go back, review limit supremum, limit infimum. Remember that we're talking about the supremum of the set of these terms from some capital N onwards, or the infimum of the set of these terms from some capital N onwards, and we're always looking at what happens to the limit as that capital N gets higher and higher and higher and eventually goes to infinity. So again, converges if the limit supremum of this ratio is less than 1, diverges if the limit infimum of that ratio is greater than 1. The root test, consider we have some series here. We're always evaluating the limit supremum of the absolute value of, that is, the A sub nth term raised to the 1 over nth power. If the limit supremum of that is less than 1, then this series converges absolutely. If the limit supremum of absolute value A sub n to the 1 over n is greater than 1, the series diverges. And if it's equal to 1, then the test gives no information at all. It's always good to note when both the ratio test and the root test do not give information. The integral test says consider a series of non-negative terms for which the other tests seem to be failing. In the event that you can find a function, f of x, such that f of n equals a sub n for all n, we may look at the behavior of this function's integral to tell us whether the series converges. Well, let me do a quick example here. Let's talk about this series. 1 plus a half plus a third plus a fourth plus a fifth plus a sixth, so on and so forth. That's the harmonic series. Now, this can be written as the following there. And what I'm going to do is I'm going to compare it to the integral of 1 over x. Now, let's take a look here. I can sort of picture each of these tick marks is, that tick mark is at 1, this tick mark is 2, this is 3, 4, so on and so forth. I can picture the terms of my series on this function graph using the left and right hand endpoints. So note that if I draw the left hand sum in here, this first rectangle right here is a rectangle that is length 1 and height 1, because this is where the function value is right there. This rectangle here has width 1 and height 1/2. This one has width 1 and height 1/3, and so on and so forth. I'll even write 1 over x equals f of x here. Similarly, I could take a look at the right-hand endpoints. And so that first red rectangle right here is 1, there's a half, there's a third, there's a fourth, so on and so forth. But the one that's really useful to me happens to be the blue set of rectangles. And you might wonder, why is that? Why are those useful? And I say, let's take a closer look at this. These blue rectangles help me to envision the terms of my series. And so what I'm seeing here is that the blue rectangle, the terms of my series, are greater than the area under this curve from 1 to infinity, this improper integral. And I happen to know that this integral diverges. And so since my blue rectangles, which represent my series, are greater than this improper integral, which is divergent, my series will diverge as well. Now you might be saying, well, what about those red rectangles? You fit the terms of the series underneath the curve. And I'll say, you're right. The relationship of the red rectangles is also true. I've just shifted everything over to a right-hand estimate, so to speak. But here's the thing, is that I say, hey, look, the second term onwards in the series is less than the improper integral from 1 to infinity. From the second term onwards, I know that my series is less than something that diverges. And remember, based on the comparison test, when I said it's not useful, we can't draw a conclusion by saying something is less than something that diverges. Same thing happens here. It could still diverge. It could converge. We just have no idea. I need to look at the alignment that gives me the appropriate relationship by which I can actually conclude something from it. If the improper integral of the function converges, the red alignment is going to be more helpful to me because it says, hey, from the second term onward, less than something that converges, so it's also going to converge, and adding that first term on there is not going to change that. But if I have an improper integral to compare it to that diverges, this blue alignment is going to tell me that my series also diverges. And that's what's happening with this harmonic series, that the area of these rectangles is equal to the terms of the series, and so we can say, hey, look, this infinite series is going to be greater than whatever the value of this improper integral is. And the improper integral is divergent, which means that my series will be 2. That's all that this is saying right here. We also have the alternating series test. If the absolute value of each term in an alternating series is decreasing and has a limit of 0, then the series converges. That is excellent. What is an alternating series? It is a series where the terms alternate in sign, and I mean strictly alternate. One positive, one negative, one positive, one negative. So plus, minus, not like plus, plus, minus, plus, minus, plus, minus. It needs to be exactly 1, 1, 1, 1. But the only criteria that alternating series need to have in order to converge is that the absolute value of their terms is decreasing and has a limit of 0. And that's that. Those two things. Our very last topic is going to be power series. And power series are series that are the following form, where we have some real number coefficient and then x raised to the nth power. So we start off with x being raised to the 0th power. So it's just going to be a real number by itself in the first term. Then the second term will have x raised to the first. The third term will have x squared. The fourth term will have x to the fourth. And of course, this is assuming that the coefficients are non-zero. So you may have some hint that have x raised only to odd powers or x raised only to even powers, because a couple of these coefficients may be 0 or something like that. But this is just a very general form here. And a power series defines a function of x whose domain is the set of values of x for which the series converges. Very, very important note that the domain of a power series is only the values of x for which the series converges. And that definitely depends on the coefficients. So there are 3 possibilities for the domain of a power series. It could converge no matter what value you put in for x. It could converge only when x equals 0. Or it could converge for all x in some interval centered at 0. And that interval could be open, could be from negative r to r. It could be closed, including negative r and positive r, or it could be a mix of the two. One of these should be like this. So the number r is called the radius of convergence. And frequently, this series converges absolutely in the interior of the interval, but the convergence at an endpoint is only conditional. And remember that conditional convergence means that if you allow the terms to change in sign when the original series has some positive, some negative terms they change in sign. When you allow that to happen, the series converges, but if you actually took the absolute values of all the terms and turned that into a series, it stops being able to converge. That's conditional convergence. So a lot of the time with these types of series, you'll find that within the interior of the interval of convergence, you will find that it's absolutely convergent, but on the endpoints, it frequently is only conditionally convergent. And we will be experimenting much more with that in the coming weeks.